Bismillahirrahmanirrahim. Last time we finished the lecture with the definition of the orthogonal vectors, and we say two non-zero vectors A and B are said to be orthogonal if their dot product equal to 0. And orthogonal means they are perpendicular. They have or they make an angle equal to 90 between the two vectors. For today, we are going to speak about the direction cosines and component of a vector A on another vector. With the direction cosine, we mean that we say direction cosine or cosines of a vector A with components A1, A2, and A3. This is a vector in three-dimensional space. Y, X, and Z. And we have a vector A. Vector A, since it is in the three-dimensional space, it makes an angle between the three axes. This is, let's say, alpha with Y, beta, and with Z, it is gamma from angle. So the cosine for direction cosines for the vector A are given by cosine of alpha equal to A1 divided by the magnitude of A. Cosine beta equal to A2 divided by the magnitude of A, and cosine gamma is A3 divided by the magnitude of A. For example, let's find the direction cosine cosines of and direction angles also. Of the vector A equal to I plus 2j plus 3k. Let's find the direction cosines. So first of all, we need to find the magnitude. Magnitude of A equal to square root of 1 plus 4 plus 9 to the square of the components. The components are 1, 2, and 3. This is equal to square root of 14. This is the magnitude. So cosine alpha equal to A1 divided by magnitude of A is equal to 1 over square root of 14. This is the direction cosine. It means alpha will be cosine inverse of 1 over square root of 14. This will give me the measure of the angle alpha. Second one, cosine beta, which is A2 divided by magnitude of A that is equal to 2 over square root of 14. So beta will be cosine inverse of 2 over square root of 14. Third one, cosine gamma equal to A. 3 divided by the magnitude of A, that will be 3 divided by square root of 14. So gamma will be cosine inverse of 3 divided by square root of 14. So these are the direction cosines and the direction angles of the given vector A equal to I plus 2j plus 3k. Now for the second part, or second point, is the component of a vector A on another one. Say of A on a vector B, denoted by component of vector A, and B will be like the base. So we are using B like the base, similar to the logarithmic function. This is the log of A with base B. This is a component of A on the vector B is given by A dot multiplied by 1 over, or dot product, B. Or it is A dot B divided by the magnitude of B. You can notice one thing. This one is the normalization of the vector B. So I can say also another form, it is equal to A dot the normal unit of B, or the normalization of the unit B. Use this notation to say this is the normal or normalization of the vector B. Take example for this one. Let A equal to 2I plus 3J minus 4K, and B equal to I plus J plus 2K. And to find A, let's find component of A on B. Component of A on the vector B, which is equal to A dot B divided by magnitude of B, equal to A dot B, the first one, 2 multiplied by 1 is equal to 2, plus 3 times 1 equal to 3, plus minus 4 times 2 is minus 8, divided by Magnitude of B is 1 plus 1 plus 4. This is equal to 5 minus 8 equal to minus 3 divided by square root of 6. So this is the component of the vector A divided by on the vector B, which is equal to A dot B divided by the magnitude of B. Now let's find the component of B on the vector A. To find the component of B on the vector A, which is A dot B over magnitude of A in this case. That will be minus 3 divided by magnitude of A is 4 plus 9 plus 16. So it is minus 3 divided by square root of 29. You can see these are different. Component of A on B is different from component of B on A. Now, next point is the projection of a vector A on vector B. Of A onto vector B. The projection given by projection of A is equal to, it is component of A on B multiplied by 1 over magnitude of B multiplied by vector B. Now the component of A is equal to A dot B divided by magnitude of B. The component of A multiplied by 1 over magnitude of B multiplied by vector B. So it can be written as A dot B divided by magnitude of B square multiplied by B. That is A dot B divided by magnitude of B square multiplied by the vector B. Notice one thing, this quantity A dot B divided by magnitude of B square, this is a scalar. This is a scalar. A dot B divided by magnitude of B square is a scalar value. And as we mentioned before, Magnitude of B square is just B dot B. It is B dot B multiplied by the vector B. And be careful, this one and this one, this cannot be cancelled. This is not correct to cancel these vectors. So don't do it. So the projection of a vector A onto vector B is given by A dot B divided by B dot B multiplied by the vector B. For example, find the projection of A given by 4i plus j onto vector B that's equal to 2i plus 3j. I need to find the projection of A onto B. So the projection of A onto B, which is equal to A dot B divided by, say, magnitude B square. Multiplied by the vector B. That's equal to A dot B. 4 times 2 is 8. 1 times 3 is 3. That is 8 plus 3 divided by magnitude of B square. It's just the square of the component. It is 4 plus 9. Multiplied by the vector B, that is 2i plus 3j. Will give me 11 over 13 multiplied by 2i plus 3j. So this is the projection of A onto the vector B. And you can see the difference between the projection and the component. The component is just a scalar value. If you go back to compare between the component, see the component is just a value, it is not a vector, scalar value. But the projection of the vector A onto the vector B will give me a vector. You can see this is vector. So the projection is a vector, but the component of A on a vector B is a scalar value.